Welcome to G Fun Facts Online. Have you ever thought about how your phone or laptop communicates? It receives a signal, a stream of digital ones and zeros, and then a separate processor crunches those numbers to make sense of it all. It's a two-step process. Listen, then think. But what if a device could do both at the same time? What if it could think with the radio waves themselves? This isn't science fiction. It's the frontier of chip design, a concept we can call the microwave brain, the revolutionary idea of merging communication and processing into a single, intelligent unit. This fusion is set to redefine everything from our mobile networks to the cars we drive and the satellites orbiting our planet. Today, we're diving deep into how this technology works and the 4 key areas it's poised to completely transform. First up is the very future of wireless communication, 6G. While 5G is still rolling out for many of us, engineers are already deep into planning its successor. 6G is not just about faster movie downloads. We're talking about a leap in capability aiming for even higher data rates, latency so low it's nearly instantaneous, and the capacity to connect a truly massive number of devices simultaneously. Think holographic communication, city-wide augmented reality overlays, and remote surgery that feels immediate. To achieve this, 6G has to push into uncharted territory on the radio spectrum. It will operate in extremely high-frequency bands, like millimeter wave and even the sub-terahertz range. Here's the problem. At these incredibly high frequencies, the physics gets tricky. Signals become weaker, more easily blocked, and traditional chip designs, with their separate communication and processing parts, just can't keep up. They become inefficient and generate too much heat. This is where the microwave brain concept shines. By processing these high-frequency signals directly in the analog domain, before they're even converted to digital ones and zeros, these new chips can handle the challenge with ease. Companies are already laying the groundwork. Qualcomm's Snapdragon X85 modem RF system, for instance, is explicitly designed to be 5G Advanced ready, which is the stepping stone to 6G. These chips integrate AI directly with the radio frequency, or RF, components. This integration enables some incredible new abilities. The first is intelligent beamforming. At high frequencies, signals behave less like a floodlight and more like a laser pointer. They're highly directional. An AI-powered RF chip can instantly calculate the optimal path for that laser-like beam to reach your device, dodging obstacles and steering the signal in real time. This maintains a strong, stable connection, even in a crowded stadium or a busy city street, where signals are bouncing everywhere. Second, this leads to enhanced spectrum management. Imagine the radio spectrum as a massive highway system. With 6G, that highway will be filled with trillions of cars or devices. AI can act as the ultimate traffic controller, intelligently managing the airwaves. It can identify unused lanes or frequencies in real time and dynamically allocate them to devices that need them, avoiding interference and maximizing the efficiency of the entire network. Finally, and perhaps most critically for future applications, is the reduction in latency and power consumption. By processing data directly at the RF stage, these chips eliminate the delay of sending data back and forth between different components. This near-instantaneous response is absolutely vital for real-time applications, like augmented reality, where a lag between what you see and what the system displays can be disorienting. Or even for remote surgery, where a millisecond can make all the difference. Furthermore, this direct processing is far more power efficient, which is a massive win for the battery life of our future phones, wearables, and sensors. But this revolution isn't just about faster phones. The second major area being transformed is the Internet of Things, or IoT. The grand vision of the IoT is a world woven together by trillions of interconnected smart devices. From tiny sensors in factories and farm fields, to medical monitors on our bodies and smart appliances in our homes. For this vision to become reality, these devices have to meet three strict criteria. They must be small, cheap, and extremely power efficient. You can't have a crop sensor in a field that needs its battery changed every week. This is another perfect application for chips that merge communication and processing. A high level of integration naturally reduces the physical size and manufacturing cost of the chip. At the same time, their energy-efficient architecture means a tiny sensor could operate for years on a single small battery. This enables a powerful concept known as edge computing. Traditionally, an IoT device like a security camera would capture raw data, in this case, a constant video stream, and send it all to a powerful server in the cloud for analysis. This consumes a huge amount of bandwidth and power. With a microwave brain-like chip, the device can perform the analysis locally, right there on the edge of the network. For example, a smart security camera could analyze its own video feed in real time. It wouldn't just stream video, it would understand it. It could identify the difference between a falling leaf, a passing car, and a person approaching the door. Only when it identifies a genuine event of interest, like a potential intruder, would it send a specific alert and the relevant video clip to the cloud. This saves massive amounts of bandwidth, reduces latency for faster alerts, and greatly enhances privacy, since most of the raw data never leaves your device. The applications are endless. In a smart factory, sensors embedded in machinery can listen for telltale vibrations or monitor temperature changes. Using their integrated processing, they can predict a mechanical failure before it happens, allowing for proactive maintenance and preventing costly downtime. In our homes and on our bodies, a fitness tracker could do more than just count steps. It could analyze your gait in real time to offer feedback on your running form. A smart refrigerator wouldn't just know it's full. It would monitor its contents, track expiration dates, and maybe even suggest recipes. Low-power, intelligent chips will make our entire environment more responsive and helpful. From the network and the home, we move to the road. The third major domain is autonomous systems. Self-driving cars, drones, and robots are not just machines, they are perception engines. They rely on a constant, massive stream of data from a suite of sensors, cameras, LiDAR, and especially radar, to see and understand their environment. Automotive radar is particularly important. It operates at high frequencies, around 77 GHz, and is essential for detecting other vehicles, pedestrians, and obstacles, especially in conditions where cameras might fail, like fog or heavy rain. The integration of RF and processing is absolutely critical here. Advanced RF systems on a chip, or RF SoCs, are enabling the development of far more powerful and compact automotive radar systems. This leads to high-resolution radar. By processing radar signals with greater precision and speed directly on the chip, a vehicle can create a much more detailed and accurate picture of its surroundings. It's the difference between seeing a vague blob ahead and identifying it as a car, a bicycle, or a pedestrian, and tracking its movement with high fidelity. But one sensor is never enough. This is where sensor fusion comes in. An AI-powered chip can take the high-resolution radar data and fuse it in real time with information from other sensors like cameras and LiDAR. It cross-references the data streams to build a single, robust, and highly reliable understanding of the vehicle's surroundings. This is a crucial step towards achieving higher levels of driving automation, where the car's perception can be more dependable than a human's. Beyond just seeing, these chips will also allow cars to talk. They will power vehicle-to-everything, or V2X, communication. This technology allows cars to communicate directly with each other, with the smartphones of nearby pedestrians, and even with smart city infrastructure like traffic lights. A car can receive a warning that another vehicle, hidden around a blind corner, has just slammed on its brakes. This cooperative awareness, powered by companies like NXP Semiconductors, who specialize in these automotive RF SoCs, will make our roads dramatically safer. Finally, we look to the most demanding environments of all. The fourth area of revolution is space and defense. The harsh, remote, and high-stakes nature of these fields makes them fertile ground for this highly integrated technology. Take satellite communications, or SATCOM. Satellites require electronics that are not only highly efficient and reliable, but also hardened against the intense radiation of space. Heterogeneous integration, a key technique in building these microwave brains, allows engineers to combine high-power RF components needed for long-distance communication with robust digital processing, all within a single compact, lightweight, and radiation-hardened package. More than that, chips with integrated AI could enable satellites to autonomously manage their own communication links, rerouting signals and processing data on board, drastically reducing the reliance on ground stations and making our satellite networks more resilient and intelligent. In the defense sector, the ability to rapidly analyze the radio spectrum is a matter of tactical survival. This is the world of electronic warfare and signals intelligence. An advanced receiver built around a microwave brain could scan a vast range of frequencies in real time. It could instantly detect, classify, and perhaps even begin to decode unknown or hostile radio signals, providing a significant tactical advantage on the battlefield. Of course, the road ahead is not without its challenges. Scaling these complex, integrated chips for mass production, developing new materials that can handle these extreme frequencies, and creating the vast software ecosystems to support them will require immense effort and investment. Yet, the trajectory is clear. For decades, we have treated communication and processing as two separate worlds. That era is coming to an end. The artificial wall between the radio and the processor is crumbling. We are standing at the cusp of a new age, where our electronic devices will not just be tools for accessing information, but intelligent partners that can perceive, process, and interact with the world in a way that is as seamless and natural as the radio waves that carry our messages. The microwave brain isn't just a clever name for a chip, it's a glimpse into a truly connected and truly intelligent future. Thanks for tuning in to Fun Facts Online.